Hey CactusCon, Alex here again. Our next talk is stealing a password through interpretive dance and other wild video game hacks. Brought to us by Dan Alt F4 Petro, who's a lead researcher at Bishop Fox, and according to him, loves to hear himself talk. So if you love to hear him talk, watch this presentation and then stick around for a live Q&A. Click the link that pops up on the screen at the end of the YouTube video and enjoy.
Hey everybody, I'm Dan Petro. You might know me as Alt F4. I'm the lead researcher and a longtime pen tester at Bishop Fox. And today I'm going to show you some really cool video game hacks that I found across various online Super Smash Bros. And Magic the Gathering programs and libraries. Now, I play a lot of video games. I always have, but these days being cooped up inside even more so. In particular, I've been spending a lot of time programming on some fun side projects. And you know what? Computers just have this weird way of breaking around me. Andrew Wilson, my old boss and former founder of CactusCon, likes to say that my methodology for pen testing is just to be so bad at using computers that they break around me, which I choose to take as a compliment. Funny enough, none of the stuff that you're going to see in this talk was from a bug hunting expedition. The vulnerabilities I'm going to show you are the result of me just tinkering with technology and on some personal side projects and being unable to do anything other than come at it from a security-oriented mindset. And I think they're pretty cool. So let's jump into it. The first bug I'm going to show you has to do with online games of Super Smash Bros. Melee for the Nintendo GameCube. Melee is a great game and esport. I started playing Melee back the day it came out in 2001. I've been hooked ever since. Over the years, I've been a player, a tournament organizer in the local Phoenix area, and these days I help out with Slippy development behind the scenes, but I'm getting ahead of myself. You might be thinking, wait, the Nintendo GameCube? Wasn't that a 20-year-old console with zero internet connectivity? What net play are you talking about? So let's take a step back for a minute and talk about that. Since around 2015, I've been working on this project of mine called SmashBot. It's an AI that plays Melee and aims to be kind of like a playable TAS. It's meant to showcase what's possible in the game at the absolute highest level while beating its opponents senseless. It can do things that are possible in the game, but not realistically performable by humans, like the infinite wave shine combo that you're seeing here. People have known theoretically about this kind of technology for a long time due to the great work of tassers like Super Doodle Man and Practical Tass, but those were only in pre-prepared videos. You couldn't actually play against those like SmashBot. So over the years, I've been slowly adding more features and updating its logic. In fact, there's loads of people in the Smash community that know me just as that SmashBot guy, and have no idea that I'm also a professional computer hacker. I've also been working on libmelee, which is an open API that you can use to make your very own Melee AI. It's basically all the laborious plumbing components underneath SmashBot that aren't actually like AI logic. Things like reading the game state and configuring and setting up a match and programmatically taking actions on a virtual controller, that sort of thing. There's a bunch of awesome AI researchers who've also been working on their very own Melee AIs using like neural networks. They're all in early development, but if you're a Smasher, keep an eye out for them. It's going to be pretty cool coming soon. So, about a year ago, right as the pandemic was starting, I suddenly found myself with a lot of spare time at home. Some of my other hobbies, like ping pong and Magic the Gathering, were no longer available. So I decided to pick SmashBot back up as a programming project, since I kind of put it down for a year or so at that point. I wanted to add console support to SmashBot, meaning having the bot play directly plugged into a real physical console as opposed to an emulator, which eventually led me to Slippy. Slippy is this wonderful project led by a developer named Fizzy that is a technology platform that added a replay system into the game. It was a crazy breakthrough that made all kinds of new applications possible, and I immediately recognized how great the tech would be and started helping out with development. My intentions at this point were really just to add some additional features that bots like mine were going to need, but then Fizzy invited me to the private beta of a secret project he's been working on in the background, Slippy Rollback Netcode, a way of playing nearly lagless online games, just at a time when the community needed a good online mode the most. So let's talk a little bit how this netcode works, because it's going to matter for our bug. Two players using the Dolphin emulator can play a game of Melee on their own computers, independent of one another. That part is easy and has actually worked for years. It's hooking them up together that's the hard part. What Slippy does is send button presses, called pads for short, short for game pads, one of these things, out over the internet to the other player. So when you press the A button, the button press is sent out over the internet and interpreted on the other end as if the player were sitting there right next to you, plugged into your console. So it's actually not so much an online gameplay system as much as it is an internet-connected virtual controller system. So some things to keep in mind here as we go forward are that games of online Melee are peer-to-peer. There's no centralized server involved. And the only communication back and forth is pad data, these button presses. Another critical component to make all this work, and one that was a major source of engineering effort by Fizzy, was to ensure that the gameplay itself is deterministic. That means, given a series of button presses, the game has to behave the same way every single time. If this isn't true, then the two players desynchronize. That means you start to play two different games of Melee on each end of the internet rather than one synchronized one. How could that happen? Let me give you an example. The character Luigi has this move called the Luigi Cyclone. When you press down B while in the air, Luigi will fly upwards, helping him recover while off stage. But only if the down B is charged. To keep players from just using the move over and over again and just kind of flying around in the air indefinitely, you have to perform the move once on ground in order to charge it. If you do it uncharged, Luigi just falls like a rock. So the game has a variable in memory that keeps track of whether Luigi's down B is charged or not. The thing is, when you first start a match, the game fails to initialize this variable to 0. It starts out charged or uncharged depending on the random contents of this uninitialized RAM. So if you're playing a game with Luigi and you press down B at the start of a game, you might go flying upwards in the air on your screen, but on your opponent's screen, you could fall downwards. This is called a desync, since you've stopped playing one synchronized game of Melee over the internet and now playing two different desynchronized games on two different machines. So Luigi's Cyclone had to be modified to never start the game out with a charged down B. Sorry, Luigi players. And this is just one of the many dozens of these desyncs that Slippy's had to deal with over the years. Okay, so this is where the first bug starts to come in, one that I call stealing a password through interpretive dance, which, by the way, is the second coolest data exfiltration mechanism that I've built over the years. I can't talk about numbers 1 through 3, but I digress. The thing that makes Slippy's netcode different and better than previous netplay implementations is that it uses a rollback system. The whole details on how this works is kind of complex, and I won't totally get into it here, but the gist is that it seamlessly handles network lag spikes by being able to dynamically revert, or roll back, the state of the game when new game pads come in from your opponent. So suppose that you're playing a game and then a network lag spike happens. So it's time to process the next frame of the game, but you haven't actually received the pad data for your opponent yet. How should you proceed? Two ways of handling this are, one, the delay. Halt the entire game until the opponent's gamepad gets there. This produces a jarring effect as the game constantly stops and then starts again every time there's a tiny network lag spike. And in practice, it's miserable to play. Tiny micro delays happen constantly throughout the course of the match, just making it awful. Strategy number 2 is to just keep going and then roll back later. So what you do is you make an assumption about what the opponent's gamepad is going to likely be. Basically, just assume that they will keep pressing the same buttons they pressed from the last frame. Most of the time, that's going to be true. And if your guess turns out to be wrong, then you roll back to an earlier state and then stick the now correct inputs in there, fast forwarding it up to the present. I know that's a lot to take in, but the end result is that the game never freezes when there's a network lag. It provides a buttery smooth experience that frankly just seems like magic. But let's dig further into how this works at the networking level, though. Because this whole system is set up to keep latency as low as possible, as physically possible between the two players, we can't just use a TCP connection. The fastest way to send packets back and forth is raw UDP packets. In practice, Melee uses the eNet library for this, and more on eNet later, but for now you can just imagine it as raw UDP packets, which it basically is. So this means that each pad is sent out over the internet, also has to come labeled with the frame in which it's supposed to meant to apply to. You see, UDP packets can get lost and just never arrive. They can come in out of order, just be routed around the internet in weird ways. So the payload itself has to describe how it's meant to be used. So your machine might say something like, hey, this is frame number 17. I pressed the B button and down on the control stick, serialize that into some compressed like binary form, of course, and send it out over to your opponent. Makes sense. The last little wrinkle in how this works that you need to understand is an important efficiency hack. Each pad is also sent along with every other unacknowledged previous pad. Melee pad data has a system of acknowledging received data, kind of like how TCP does it, but unlike how TCP would, we can't afford to just sit around and wait on pads when it's time to send them. So suppose we press a button and send the pad out. We're playing a game with an opponent. Then 16.66 milliseconds go by, the duration of one frame of the game, and it's time to send our next pad out to the opponent. But wait, we never got an acknowledgement that the last pad was received. It might have gotten lost out on the open internet. We need to resend it. So what we do is we package the previous pad along with this one, sending them both together in one packet. This can actually keep accumulating if pads are never acknowledged, in practice up to a maximum of 7 frames behind. Okay, so let's take a peek at the code responsible for reading pad data, now that we know how all this works. This is the onData function of the Slippy netplay class. This is what gets hit and reads the raw data packets when they come in. So the code here does is it peels off some initial values like this message ID here that tells us what kind of packet this is, and then the packet's frame index. There's some timing logic that isn't particularly relevant to us, and then if we scroll down just a little bit, we loop over the pads, because again, there's potentially multiple pads inside of this packet in this section right here. The code queues up the pads that we just read and sends them to the game as button press inputs, and then sends out an acknowledge message that we received this packet. Okay, if you want to pause, try to see if you could spot the bug yourself. Okay, so this packet data variable right here is the raw pointer to the memory contents inside the packet. We then iterate over this data, inputs to copy number of times, reading pad data from the buffer at each step. The head frame variable here is just the last received frame from the opponent, the thing that we're expecting. So for instance, a head frame here might be 10. That means the last packet we got in was for frame 10, and now we're expecting frame 11, or perhaps something higher, because again, there could be multiple pads here. So if the frame variable were 12, we would loop over the packet twice and read 2 pads from the buffer, send them to the game, acknowledge them, and be finished. Critically though, the logic here doesn't check that the packet actually contains the data that it claims to. The opponent can send a packet with a frame number of anything. So if you insert some huge value here, something in the billions, your opponent goes haywire, reading data out of the boundaries of the packet buffer until it inevitably goes out of bounds entirely, causes a seg fault, and crashes. So let's do that. What I built right here is a modified version of the emulator that will send a packet to my opponent, claiming to be frame 1 billion anytime I press up on the D-pad. What happens when I do that is my opponent's computer sees a packet for frame 1 billion and assumes that it must therefore contain 999,999,000-ish pads. So it tries to read that many pads from the buffer, running way over, causing a crash. Check it out. Segfaulting your opponent's game at will is pretty cool, but we can do better. What's happening here is a read overflow into heap data. In particular, remember that the process is trying to read controller pad data from that buffer. So if we give it a Goldilocks overflow that's not so long as to segfault like before, we can trick our opponent into reading random data off the heap and interpreting it as our own button presses in the game we're playing together. Also, in the Slippy ecosystem, each player has their own play key, which is basically their account's password. You log into the Slippy system using that key, and if someone were to steal it, you could play under their account. This is read from file when you first start up the game and is stored onto the heap. So the opponent's password is basically there lurking around somewhere on the heap, waiting to be read. So what I'm going to do here is modify our payload from before. Rather than set the frame index to 1 billion, we're just going to increment it by 10. That means the opponent will read only 9 pads out of bounds, keeping it from segfaulting. Let's see what this looks like. Here we are playing an online game of Melee again. The attacker's screen is on the right and the victim screen is on the left. Every time I press up on the D-pad here, the payload launches. So as you can see on the right, my character taunts, which is what's supposed to happen. But on the left, something random happens each time. But it's not actually random at all. The actions it takes are arbitrary heap contents interpreted as pad data. As you can see here also, we've desynchronized. The game is different on each screen, but we're still connected to each other and sending pads back and forth. All we need now is a way to exfiltrate this data. We need a way to look at those random movements our character is making on the opponent's screen. But this is kind of tricky. The game is desynchronized, and we can't directly see our movements our character is taking on our opponent's screen. So while our character is moving around randomly on the opponent's screen, disclosing sensitive data in the process, we can't see it. Our screen just shows the character is acting normally. So how do we get the loot? There's two ways. First, the easy way. Remember when I said that I was working on Slippy to put in some features that Smashbot would need? Well, one of those features was a spectator mode. In order for Smashbot to work, it needs to see the game live as it's running, which didn't exist at the time. This eventually became the spectator server that Melee tournaments use to broadcast online games. So the easy way to exploit this would be to target someone who is broadcasting, such as someone who's playing a tournament match. You used to be able to see the full list of broadcasting users just by logging in right here. But today you can only spectate a match if both ends have specifically opted in. Good security move. But if you're spectating a game of Melee, you're sent the full state of the game from that player's perspective at each frame of the game, including the raw pad data that we really want. When the game is finished, the spectator client creates an SLP replay file that contains all the binary data of the match. So we can just write a little quick Python script here to pull out all the raw pad buffers from the game and throw them into a hex file, and voila! Random heap contents from your opponent. Oh, and what's this? A play key. And then there's the hard way. There's one other way of looking at our opponent's screen, of course. Loads of people regularly stream themselves playing games of Melee on twitch.tv. Basically, every tournament, professional and amateur players stream their perspective of playing through the event for others to watch. So if we play against someone publicly streaming like this, we can launch our exploit like before. Only this time, we don't have access to the raw underlying binary pad buffers. Instead, we have to infer them from the video game actions taking place. We have to interpret the interpretive dance taking place right on screen. Each pad takes 8 bytes of memory. They're stored like this. There's 2 bytes for the digital buttons, A, B, X, Y, start, etc. There's 2 bytes for the 2 analog sticks, the control stick and the C sticks, X and Y positions. Then 2 bytes for the L and R analog triggers. So each action that takes place, each frame, tells us about the 8 bytes in memory there. So looking back at our example earlier, right here our character pauses the game. That means the start button must have been pressed, but we don't know anything about the other buttons. Shortly after, while in the pause screen, the camera doesn't move. That means during these frames, the control stick and the C stick weren't being pressed, since that would move the camera. So we know those were 0. When we unpause, the start button must have been pressed, followed by a neutral B attack, which means the sticks were 0 again, and the B button was pressed, but not any other buttons. So yeah, there's not a great way to write a tool to automate this process, since you need to go frame by frame through the video on screen. But the data is right there, dancing in front of you. So this is a funny story. We fixed this bug. I wrote some code right here that checks incoming packets to make sure that they actually contain the data that it claims to. Simple bounds checking, really. Nothing fancy. I sent out a pull request to the project for this code. It was merged in, and shortly after, pushed out to users in the next release. And then, everything broke. Within minutes of releasing out to the world, we got widespread reports of games disconnecting right when you start. We tracked it down, and lo and behold, it was my code that was causing the disconnect. I was astonished. The bounds checking was so simple on the code. How could I have screwed that up? So I dug into it further and discovered something funny. It turns out that my code was working just fine. What was happening was that when games first start, they don't start out by sending frame 1. the game has a local packet buffer, which I'm not going to go into depth on here, but it causes the game to start at frame 3 or 4 typically. So whenever a new game would start, the very first frame that it would send out would be for frame 3, but only contain one pad. That means the receiver was expecting it to contain 3 pads. So my bounds checking code correctly identified that this would overflow the packet buffer and tossed it out, disconnecting the game in the process. But this means that this was normal behavior for Slippy games. Almost every game of online rollback net play for Melee, up until this point, started out by overflowing the packet buffer and reading random heap data as pads. But nobody noticed this up until now, because for the first 180-ish frames of the game, you can't move. You're in this kind of state where you're waiting for the ready go sign to disappear. So the game is technically started. You're sending pads back and forth, but your controller doesn't move your character. So the random heap data doesn't cause a desync. But the overflow does happen, and the data is there. After every game of netplay, the game stores an SLP replay file of your match. Just like before, this contains the raw pad buffers at each frame, and people like to share these files around to like show cool matches to their friends and stuff like that. But each of these files now contain little bits of potentially sensitive fragments of your heap. So I'm working on making a scrubbing tool to zero out any pad data at the start of a replay file, just for the first bunch of frames. That way you can run it against your replay files to make them safe to share again. Also, the bounds checking code got properly fixed so as to make clients always start setting from frame 1. And that's where the bug stands today. Let's circle back into something that I mentioned earlier, the enet library that Melee uses for sending pads back and forth during games. Last time I talked about it as raw UDP packets, but that's not completely true. Let's dig into that. First, you've got to understand what enet does, and just as importantly, what it doesn't do. Networking is really complicated, and if you let it, it'll scope creep way out of proportion and wind up being an all-encompassing library that affects every aspect of the programs that use it. So in general, enet does actually a great job of avoiding this trap. It does what it sets out to do and then stops. This is admirable and should be exactly what you're looking for in a software library. The thing is, games need low latency communication. Other metrics of network traffic, like throughput, simply don't matter. Enet is rather slow, actually, if you try sending an entire gigabyte across. But why would you do that? That's not what it's for. It's for sending small pieces of data, like gamepads, over the internet with as little latency as possible, with as little overhead as possible, while maintaining some quality of life features that you wouldn't want to have to implement yourself. In particular, enet manages the concept of a connection, despite being in UDP, which is not otherwise connection-oriented. On its own, UDP has no connections. It's just individual packets being sent around with no guarantees for delivery. So with enet, you can tell if the other end has disconnected from you, which is a thing that games really want to do in general. It also has an optional reliable mode that ensures packets actually do arrive and in the correct order that you sent them. Now, you might be thinking, why doesn't this guy just use TCP? Doesn't he know that TCP does all that stuff? Well, in a perfect world where data never gets corrupted in transit, sure, but in that world, we wouldn't need networking protocols. The problem with TCP is how it deals with a mangled packet. TCP waits a predefined amount of time before resending any unacknowledged data, and it uses an exponential backoff too. So on Linux, the first timeout is about 200 milliseconds, which means that if you send some data and it doesn't get acknowledged after 200 milliseconds, it'll resend it. 200 milliseconds might sound fast, but Melee runs at 60 hertz, meaning a single frame lasts 16.66 milliseconds. So if a single packet gets mangled and then needs to be resent, it won't happen for a full 12 frames that pass by. And if that resend screws up too, which can easily happen, the next resend won't happen for another 400 milliseconds. Meanwhile, the entire data stream is ground to a halt while you're waiting for these timeouts, because TCP has to maintain the order of the data. So no, we don't want to do that. If the pads get lost or mangled, we'll just resend it next frame like we had before. Don't hold up the whole party for it. So if you want low latency communications, TCP is just not for you. Okay, so like I said, enet has this concept of a connection, established using a three-way handshake, not unlike TCP's. And this is where the first enet bug comes in. Enet is small, and that's on purpose. It wants to have a small and predictable memory footprint. Enet doesn't just run on gaming PCs with gigs of RAM to deal with. It has to run on old gaming consoles like the Nintendo Wii and other embedded environments where memory can be scarce. So what it does is it lets you define how many peers you want and then allocates memory for those peers all at the beginning. So this works pretty well in a peer-to-peer environment. Like if you're playing an 8-player game, you'd assign memory for 7 peers and then connect to them all individually. This starts to break down, however, once you have a client-server architecture, one that can have n peers. For example, in the Melee ecosystem, there's a matchmaking server that's used to do NAT hole punching and just general matchmaking things. It's a public server that you connect to and queue up to play a match. And this uses eNet. But eNet can only handle a hard-coded maximum of 4,095 peers, which means that if you connect to any eNet server 4,905 times, the 4,906th attempt will fail because all the peer slots are taken up, and it can't make any more. So causing a denial of service on the server is just as simple as connecting to it a few thousand times. But it's actually worse than that. You don't need to fully connect to the server by completing the three-way handshake. After you send just the first leg of the connection, the server takes up one of the peer slots while it waits for the connection to finish or time out. So an attacker can send an initial connect packet spoofed to come from any IP address and take the server down. There's no way to know where the attack is coming from. There's no way to ban IP addresses of the attackers. There's no way to know which are the bad requests and which are your actual users. It's completely untraceable and unpreventable as an attack. The connections won't complete, but they don't need to. The attacker can just keep sending initial connect packets to make sure the peer slots are always taken up. If you're familiar with TCP, this is really no different than a SYN flood attack. So maybe we can learn a lesson from how TCP deals with it. Let's look at what Cloudflare has to say. Cloudflare is one of the best at preventing DOS attacks and is on the front line in terms of dealing with it in the real world. So here's the Cloudflare blog describing how a SYN flood attack works and how to mitigate it. Here's the TCP three-way handshake, and right here's the attack. So you can see the attacker sends spoofed SYN packets, the first leg of the handshake, forcing the server to spend resources responding and maintaining half-open connections. It's a resource exhaustion problem, basically. Exactly the same problem we have in eNet. Cool. So what does the Cloudflare recommend? Let's see. Okay. Increasing the backlog queue. All right, so that's basically get more resources. Next is recycling half-open connections. Well, okay, it's basically use resources efficiently and get more. Then there's SYN cookies, which is kind of complicated. Basically boils down to get more resources. And that's a major problem with this attack. It doesn't have a great fix. Sure, having a hard-coded maximum of only 4,000 peers available makes exploiting it easy, but even with a significant overhaul to how eNet does memory management, the attack will still work, just marginally less effectively. So it's not like TCP ever solved this problem either. I disclosed this and the next issue to the eNet project a few months back, but for this one, the reality might very well be that a lightweight networking protocol like eNet just isn't suitable for publicly accessible servers, and is really only tenable in peer-to-peer applications. So if you're out there running a service using eNet that's publicly available on the internet, you might want to reconsider. Let's talk about IP spoofing for a second, because it's going to matter. This is lost on a lot of younger developers, especially web developers, since they're just used to this world where people can't spoof their IP. The web server can track you by your IP address and potentially ban your IP if you do something bad. People can use the VPN if they really want to hide where they're coming from, but they do actually need to route their traffic through the VPN for that to work. You can't simply just lie about what IP address you're coming from. This is not the natural state of networking on the internet. Any packet you send has the source IP address right there in the data that you as the attacker send. You can change it to say whatever you want, claiming to be from wherever you want. So why don't attackers just simply do that? Well, this is an artifact of some security provided by the initial sequence number, or ISN, of the TCP three-way handshake. The TCP handshake has 3 legs: SYN, SYNAC, ACK. That part you knew. But what's maybe less known is that there's also a negotiation on what the sequence number is to start from. The sequence number is used for keeping track of the order of packets during the byte stream. Back in the day, TCP servers used to just start with a sequence number of 0, which is sensible. But that lets attackers blind spoof their IP address. Let me show you how that can happen. Suppose you have a web server with an admin post endpoint that lets you update backend code. So if an attacker could make requests to this endpoint, they could upload arbitrary code and take over the web server. But you've whitelisted your IP address so that only that one IP address can hit the endpoint. This sort of thing happens all the time, trust me. Sensitive administrative functionality being hidden behind an IP whitelist is super common. But now imagine that the TCP server uses an initial sequence number of 0. What an attacker can do is send a spoofed TCP SYN packet claiming to come from the admin's IP address. The server then responds to the admin with a SYN-ACK packet, acknowledging the first leg of the handshake and sending an initial sequence number of 0. The attacker can then send a spoofed ACK packet for the known sequence number of 0. The connection is now in place as far as the server is concerned. It has no idea that it's not talking to the real administrator. The attacker can then shove some data down the pipe with the spoofed IP address. Using this method, you can send, but not receive, any data as any arbitrary IP address you want. So what TCP did to prevent this is to have the server randomize the initial sequence number. The attacker can send spoofed SYN packet, fine. The server will respond to the actual admin, by the way, not the attacker, with a SYN-ACK packet with a random 32-bit sequence number. The attacker now needs to ACK this sequence number, but they can't because they don't know it. They don't have any way of knowing what sequence number is, so they can't complete the connection. Okay, now let's take a look at some ENIT packets in Wireshark. This is a capture of me playing some Melee. In particular, let's check out this packet here at the end. This is a disconnection request packet. It's what peers send to one another when they want to hang up. There's not too many fields here, so let's just go through them. There's 2 bytes here for a peer ID. It's not shown in Wireshark, but the first 4 bits are actually 4 flags. Only 12 bits are used for the peer ID itself. The next 2 bytes are a sent timestamp. This is in milliseconds from the perspective of the sender and wraps around pretty quickly. Next is a command, which is just 1 byte. This is the value to specify that this is a disconnection request. There's a channel ID, which is a dummy value here since it's not used in these meta requests. Then there's 2 bytes, which is a reliable sequence number, which, as you can see, starts at 0 and monotonically increases each message. You can probably see where this is going. There's no equivalent to TCP's initial sequence number here. There's nothing that really keeps an attacker from spoofing this packet. So if 2 people are playing a game, happily sending packets back and forth out on the open internet, a third party can send a spoofed packet to one of them, claiming to be from the opponent, saying that they want to disconnect, killing the game. Let me show you what that looks like. So what you're looking at here is a game of Melee netplay between the screens here in the middle and the right. We're just going to demonstrate a little bit that we can move back and forth and that there's a real playing game. But then I'm going to hit the Go button on an attack screen, my attack script here on the left. It's going to flood the network with lots of guesses, trying to guess the UDP source port, UDP destination port, and peer ID of one of the peers, trying to send a disconnection packet to the peer. So you can see that the game is going along just fine. We're still able to move around in synchronization. Oh, and then we've disconnected. You can see here the big red letters come up that say disconnected, means we have disconnected from the other peer. When talking about spoofing a packet like this, it's important to keep track of what information the attacker needs to know or guess in order for the attack to succeed. So let's do that. First are the IP addresses. The attacker needs to know the IP address of both players involved. This might sound like a big hurdle at first, but in practice it's really not. Your IP address is not private. Games are peer-to-peer, remember, so you disclose your IP address to everyone you play against. And you can definitely imagine some nefarious players who match up against well-known players and keep track of their IPs for later use. But it doesn't even take that. Consider the typical Melee tournament, which uses a double elimination bracket. In the grand finals, 2 players are duking it out for who gets first and who gets second. This is the major event of the tournament, and above all else, you wouldn't want something bad to happen to that game. But the player who just got knocked out prior to this is in third, and is likely to have been knocked out by both of the players that are playing in grand finals right now, meaning they played together. And that player might just have an axe to grind with them. So a salty third place finisher is a very legitimate threat scenario for this kind of attack. They have both the means and the motive. So we assume here that the attacker knows both of these IP addresses. Next are the UDP ports. The spoofed packet needs to have the correct UDP source port and destination port. There's no way to know these, they have to be guessed. By default on Linux, UDP transient ports are chosen at random between 32,768 and 60,999, meaning that we need to guess 28,231 ports each, which would be a lot, but in practice, we don't actually need to. You see, games don't want to use the full possible port range, because then you'd need to whitelist every single one of these in routers for a lot of users. And we wouldn't want to have to whitelist every possible TCP or UDP port. So for example, Melee actually just uses ports 49,000 through 51,000. So there's only 2,000 possibilities for each port that we need to guess as an attacker. Next are the ENET specific values. As it turns out, the sequence number that we saw earlier is actually not required to occur in sequential order. If you give a value out of order, the recipient is just fine with it. So we don't need to guess that value at all. My attack script just sets the value to 1 and everything's fine. The only value we need to guess correctly here is the sender's peer ID. Like I said earlier, this is only 12 bits and also isn't randomized. It's just a sequential-ish number and tends to be some low number below 4. For Melee games, it's almost always 0 or 1. Let's do some quick math here then. We need to guess 2,000 UDP source ports times 2,000 UDP destination ports times 2 peer IDs. That gives us 8 million total guesses. On average, though, we'll hit the right value in the middle, so let's have this to 4 million guesses that'll take us to do in a successful attack in the average case. Each packet is 54 bytes long, so that means the attack will need, on average, to send 432 megabytes of data. I get 35 megabits upload on my home network, which would take about 1.5 minutes of attacking to succeed. Of course, if you have fiber, that speeds it up a lot. And the attack I showed you earlier was over my home gigabit LAN, so it was real fast. But in any case, you can see that this is a quite practical attack. Lastly on this, while I showed you an example of sending a disconnection request, packet injection attacks are not limited to this. Basically, any kind of packet can be forged this way, including application-specific payloads. So if your game has a way of doing password resets in-game, for example, those could be forged too to do a complete account takeover, and that's just the start. Oof, okay, we're almost at the end. For the last 2 bugs, we're going to leave Super Smash Bros. Behind and planeswalk over to Magic the Gathering. I've been a Magic nerd for a long time. In fact, these posters behind me are Magic art by John Avon. Some of my favorite, behind perhaps Seb McKinnon. Just like before, though, I was working on a pet project to make a bot that could automate games of Magic the Gathering against itself. My motto is, why play games when you can make a bot to automate playing against them for you? I never did wind up actually completing this project, but here are some cool things that fell out of it. This one will be quick. Cockatrice is a popular open source Magic the Gathering application. Ever since the pandemic, I've been using it regularly actually. A group of friends and I play Commander Tuesday nights. Magic is a game that requires a lot of randomization as part of it. The most obvious example of this is shuffling your deck of cards. If you could know the order of your deck, which is supposed to be randomized, then you could cheat and win at a game pretty effectively. As you can see here, Cockatrice uses the Mersenne Twister as an algorithm to do all the random events server side, including shuffling a deck. The Mersenne Twister is not a secure random number generator. It starts off with an initial seed integer and then produces new integers in a completely predictable pattern from it. I even wrote a little tool here called untwister that untwists the Mersenne Twister and can recover the initial seed given a series of apparently random numbers. The end result is that it's entirely feasible to reverse this RNG seed and then cheat in your game of Magic. I disclosed this issue to the developers a few years back actually, but it was marked as won't fix. And you know what? They have a point actually. While it wouldn't hurt to use a cryptographically secure random number generator here, Cockatrice doesn't even enforce the rules of Magic for you. Cheating in Cockatrice is pretty trivial. You can just perform any game actions you want, even if they're not legal ones. The game won't stop you. It's really meant for low stakes games amongst friends, which is fair. Also, it made writing a bot using Cockatrice hard since it doesn't know how the rules work. My bot would be no good if it kept taking illegal game actions, which led me to Xmage. Xmage is also an open source Magic the Gathering application, but this one actually does rules enforcement, which would be a much better fit for the bot that I was trying to write anyway. Xmage has a client-server architecture, so I figured I could basically write my own client that would talk to the remote server and take game actions. So I went in and peeked at the source code and 1.3 million lines of code. Are you kidding me? Okay, forget trying to read the code. Let's just boot up the game and look at the network traffic between the client and server and Wireshark. I figured there'd be like a REST API that I could make calls to, make my own client for. So I started the local server and client locally here. Let's just log in using a dummy account and see what the traffic looks like. Huh, that's not HTTP. Java.lang.object. Java.lang.string. Oh no. Oh no, those are serialized Java objects, aren't they? Yep. I'm gonna have to exploit this, I guess. Xmage uses this rather abandoned project called JBoss Remoting to do network communication. It's a remote invocation library whose last release was in 2014. If allowing attackers to remotely invoke methods on your server sounds insecure, that's because it is. This kind of RMI system is perfectly acceptable between two internal components of a system, though honestly, even then, just use an HTTP API. But certainly not between a server and untrusted clients. Anyway, JBoss remoting fundamentally works under the hood by sending serialized Java objects back and forth. Not plain old Java objects, though, or POJO as they say. No, it uses an equally abandoned project called JBoss Serialization. This is a completely different and custom marshalling format. So, let's build an exploit for this. I have two working exploits to show you, or perhaps one and a half. The first is a simple denial of service. So the easiest way to make an exploit in this scenario is just to write a Java program that uses JBoss remoting and JBoss serialization and send a legitimate message over the wire. What I did here is build a hash set that recursively references itself. So when the reader tries to deserialize this object, it will spend an entire CPU spinning trying to resolve the references over and over and over. To bring down the server, you just need to send a few of these over to tie up all the CPUs it has. Check that out. Okay, there's a lot happening on the screen right now, but on the top is my CPU usage. That's what you want to watch. You can see each time I run the attack program on the bottom, the CPU usage goes up. After I've run the attack 4 times, the Xmage server process is running at 400% CPU, meaning it has 4 entire CPUs spinning, doing nothing but trying to read the hash set that I gave it. This next one is a bit more complicated. I'm going to use a modified gadget chain that WISO Serial typically uses for the Commons Collection 3 payload. It's modified because of an annoying bug I ran into. Turns out that JBoss serialization just fails to serialize certain objects. It's not a security mechanism, it just crashes on certain objects. Trust me, it was very annoying while trying to make a proof of concept when like a quarter of all the objects I ran into just fail for no clear reason. Anyway, one of the outer layers of the default WISO serial payload is one of these classes that crashes, but we can work around it. Honestly, you could probably spend an entire presentation just talking about what this payload is doing and how it works, but the gist here is that it executes an arbitrary shell command by chaining together a Rube Goldberg machine of invocation gadgets. We're only going to cheat a little bit here. The Commons Collection 3 jar that Xmage uses has been patched to prevent this exact object, the invoker transformer, from being deserialized, specifically because of this sort of exploit. It's a band-aid that doesn't really solve the underlying problem, though, but I didn't want to go to all the bother of discovering a brand new gadget chain just for this, so I went and re-enabled the Invoker Transformer class in the Xmage server. That way we could demonstrate this vulnerability in the JRE arguments. On the left here is an Xmage server running in a debugger, and on the right is our attack code. It's currently set to run the GNOME calculator as a test payload. Let's run it. Now, I just ran the calculator app using this attack, but of course, you could run any arbitrary shell command you want. I disclosed this issue to Xmage over a year ago, but fixing it would require a significant rework to how the entire application does network communication. It would need to tear out all the existing network code and design a completely new REST API or some other mechanism from scratch. And it seems like that's not likely to happen, so this issue is still exploitable today. I hope you had as much fun watching this as I had putting it together. Video games are complex pieces of technology, and we often don't give them the respect they deserve for that. Games can sometimes be dismissed as just toys, but in my experience, the average online game is more complex than the average web application. Always approach your problems with a security mindset, and trust me, things will fall out. Later.